Okay, so we seen before, we have a carbonyl carbon here. Here's our alpha carbon and our beta carbon. So you're saying that a nucleophile reacts with they can react at the H bond there, that forms an elated ion, but usually it will react at the carbonyl carbon. So do you need a strong nucleophile or a weak nucleophile if you want to remove the proton from this one?
Strong.
You need a pretty strong. Is the beta carbon involved? Can it react with a nucleophile?
When you make the 1, 2, 1 on the alpha beta.
Yeah, we know we learned how to make this alpha beta unsaturated aldehyde. We'll talk about that in just a second. So, where does an electrophile react with this compound?
Electrophile can react lone pairs on the oxygen.
Lone pair of the oxygen. So usually that electrophile is going to be H plus. Yeah, so again, like we were saying before, that just makes if you have an acid reactant here, that makes a carbonyl carbon more electrophilic.
Can an electrophile react with the alpha carbon as well after it's protonated?
With the alpha carbon? Yeah.
So if you protonate that, it makes it into an alcohol and then the hydrogen is eliminated?
Say that again?
If you protonate that oxygen,
This one?
yeah, and then the bond comes down and it makes an alcohol.
Yeah, so actually, let's do this. So if we have this compound, and then we can draw a resonance structure which looks like
Pi bond moves up to oxygen.
yeah, so the pi bond moves, forms a lone pair, and then we get plus on the carbon. Yeah, so this makes this carbon to carbon more electrophilic now. You can show that it has that plus charge.
And then if something were to react there, then that will be.
Yeah, so usually what happens is that if we have a nucleophile reactant here, so then that forms that tetrahedral intermediate we were talking about. Now, see, it depends, because usually if you have an aldehyde or ketone, it's a nucleophilic addition. Okay, so nothing leaves. So we'll get it as our product. We'll have, the OH and whatever the nucleophile could be like an hemiacetal or an acetal, or a what's it called when you have two OHs bonded to it? It's called the textbook called it a hydrated. Or you call it a Chem diol because the two OH groups are in the same carbon. Okay, what about this one?
That's with the lone pairs.
Oxygen.
Piece of air.
Okay, so where does a nucleophile react with this compound? A carbon to carbon. Anywhere else? H bonded to the alpha carbon. This one? Nope. We didn't look at that reaction. We haven't seen a reaction like that. But there's another place a nucleophile can react with this compound here. Not on the H bond, the beta carbon. Yeah, so you can either get the carbonyl carbon or
It could make the first pi electron, or the pi bond, it could make it flow.
yeah. So can you draw a resonance structure for this one?
Yes.
Okay, so what does that resonance structure look like? Okay, so let's do that. So if we have this compound here, what does that resonance structure look like? Okay, so yeah, we can do this.
Negative charge in the O. Between 2 and 3.
And plus charge on. So there's that plus charge on carbon 3. That means get the nucleophile reactivity. So that was also that conjugate addition reaction. So if you have a strong nucleophile, will it react at the carbonyl carbon or at that beta carbon? Yeah, so a strong nucleophile reacts at the carbonyl carbon. A weak one will react at that one. Okay. So it sort of depends what you want to make. Okay, so that was called that Michael reaction.
Oh, it must be Michael.
There's a donator and it's
Okay, ready to keep on going? Okay, so take a look at this one. So cholesterol is this molecule. So note that it has two functional groups. So what I'd like you to do is to predict the product of the reaction of cholesterol with each of those reactants. Now remember, we talked about how reactants react last time.
have some metal substituents or these kind of ring or products on the what are your
What is that?
Turns out to a ketone.
And it's really similar to this.
Don't touch the edges.
What is that?
That's a strong electrolyte. Strong electrolyte. Just pretty strong.
That's another carbon, right?
Okay, so remember, do the same thing we just talked about. We have an alcohol group here, so we know that the alcohol can react with either a nucleophile or electrophile. And note that we have the alkene, this pi bond here. And we know that that alkene can react with an electrophile. Since the pi bond is a nucleophile, so how does cholesterol react with HBr? Is it going to react with the OH group or the pi bond? Okay, so who thinks it reacts at the pi bond? Who thinks it reacts at the OH? Okay, so those of you who said OH is correct because note that the lone pair on the O is a better nucleophile than the pi bond there. So remember that the strongest nucleophile reacts with the strongest electrophile. Okay, so that's going to react with the OH. And what's going to be the product of that reaction? Yeah, so we'll get, so first we'll get the protonated alcohol, which means we'll have a good leading group. And then what is the Br minus group? Yeah, because we can either get a substitution product or we could get an elimination product. So if we got the elimination product, where would the pi bond go on between these two carbons or those two carbons? So what do you think? Okay, so we got the elimination product. Okay, so we write this on the chalkboard?
Yes.
Just so you're looking at all the possibilities.
Do elimination studies.
Okay, so again, the reaction with HBr, let's just write it this way. I'm not going to write the whole thing on the chalkboard. Okay, so here's our cholesterol. There's the rest of the molecule. Let's put that here. So if that reacts with HBr, note that what will happen is it will form this intermediate. Okay, so once that intermediate forms, we still have Br minus floating around in the solution. And remember that here's our alpha and there's our beta carbons. So we have H's bonded with each one. So will the Br minus react at this H or that H? Why this H?
Because it's a conjugated system.
Yeah, because note that it reacts at this one, it's going to form that versus reacts at the other one. It'll form that one. Which one's more stable?
This one's right.
Yeah, so you're saying this is more stable because it's conjugated. Okay, so you can look at those two possibilities. Now, you can also get the substitution product. So if you get the substitution product, okay, so there's this one. Which of these three, which one do you think is most likely to form?
BR the one on the bottom. BR substitution.
So you're saying the substitution product is most likely?
Yeah.
Why is substitution product?
Smaller base.
Br minus is small. Now look at the periodic table. So Br minus is in period 1, 2, 3, 4.
It's not the size of, say, the ethoxide or T-etoxide.
There's another reason. So remember we were talking about substitution elimination in Chem 12A? And although they compete with each other, usually what will happen is the elimination. Because really under a certain condition you can get more of the substitution product, but usually you get more of the elimination product.
Just in general, there's a computer reaction of
Yeah.
measures versus.
Yeah. Because that's, see, the problem with all these organic chemistry textbooks is they spend one chapter to talk about those SN1 and SN2 mechanisms. But the problem is, that's not the more, we have substitution competing with elimination, we'll almost usually get more of the elimination product. So what the textbooks really should talk about is both and say, it's only under those certain conditions you get the substitution product. I think what these authors like to do, they like to talk about the mechanisms. You know, you have a first order nucleophilic or second order nucleophilic, and you like doing all that stuff. But really, you know, if it's up to the chemicals, they don't really care whether it's SN1 or SN2. They just know it's a substitution. You get the substitution product in the major product. Okay? So when cholesterol reacts with Br2, what's the product?
You VR next to the OH or VR on the other side of that out.
So you're saying the Br either reacts at the beta here, or reacts
The other side of the beta.
on here?
Yeah.
It could react across the
Or,
alkene as well.
yeah, it can react across the alkene, because that was the addition reaction we focused on in Chem 12A. Because don't we need specific conditions we want to react here or there? Or actually over here? Actually, it's got to be here. Because what did we need something else besides Br2? We needed light. Or we could use NBS too. So again, if it's just Br2, it's going to react across the high bond.
So wait, MBS, is that called a hydrocorrelation?
No, NBS is that N-bromosuccinimide. That's that specialized brominating reagent. No, that's different than so you have sodium boryl hydride, which is this compound, NaBH4. Okay, so that's that boron compound. That behaves like a reducing agent. And NBS is different. NBS stands for N-bromosuccinimide. This is a ring compound. We have a nitrogen bond to a bromine, so then it actually behaves like sort of a radical type of reaction.
So when you add MBS, it makes it so it's only the bromines are going to more substituted condition?
For NBS, it depends. Because we looked at, there was 2 or 3 reactions we looked at with using NBS. But this was really, whenever I see NBS, I know it's going to brominate something. I just have to figure out what it's brominating. Okay, so again, NBS is some sort of brominating agent. So the same thing is true when you lose, for example, like SOCl2. Because note that SOCl2, this is a chlorinating agent. That'll put a chlorine in something. So one reaction we used with SOCl2 was...
Change that OH to Cl.
Yeah, so that was this one. You have the acid group to this one. That was the SOCl2.
So those are just called halogenation reactions then?
This one? Not this one?
Both, are they just called halogenation reactions?
It's a type of halogenation reaction. But I look at these are the specialized reagents. So we didn't look at the mechanism of these because there's only, 1 or 2 very specific reactions where these work. So for the mechanisms, I'm only interested in the common ones where they apply to many reactions. Okay, what about NaOET?
Strong base.
Yeah, so the ethoxide is a strong base, so how is that going to react?
Going to deprotonate.
Yeah, so first it's going to react with deprotonate the alcohol. And is it going to do anything else? Once it deprotonates the OH?
Does the oxygen, the negative charge of the oxygen then attack the ethyl group, the alpha carbon on the alcohol that we formed?
So you're saying that, okay, so let's go back to here. So we have this one. So we have this one here, and you're saying that, then we still have, we have the ethanol.
So is that negative oxygen now going to attack the alpha carbon and then the, and obviously OH can't leave.
You would need an acid to do that. Yeah, so this is, for this one here, this would be your body.
Unless it's unless OH, unless alpha group is protonated by something else.
Right.
And there'll be elimination.
Or you can have substitution. But it's usually going to be elimination.
So it doesn't matter, like the size of the base, since it's large, it's harder to get into for substitution, right?
Yeah. Yep.
For the BR2, will you have two BRs?
Yeah, so you have a BR here, and this one, and a BR there. What about KMNO4? So that's going to convert what to what?
Alcohol to a ketone?
Yep, so that'll convert the alcohol to a ketone.
But so that came out of was a strong one and everything all the way to an acid? Or-
Now, like, yeah, because remember, what type of OH, what type of alcohol is this? Primary, secondary, or tertiary? Yeah, secondary. So whether it's KMNO4 or PCC, it's going to convert it to a ketone. So if you had a primary alcohol and used KMNO4, then it would convert it all the way to the acid. Yeah, so you write that down. Yeah, so we have a primary alcohol. Yes, if you use PCC, that's going to convert that primary alcohol to an aldehyde. Then you can convert the aldehyde to an acid by using KMNO4. Or you can go from the primary alcohol to the acid by using KMNO4. If you have a secondary alcohol, that's converted to
That one is strong.
the ketone by using,
It's also strong.
yeah, PCC or.
Mrs. G, you say?
Yeah, see, if you want to stop at the aldehyde, you want to use PCC. So if you use KMNO4, we go all the way to the acid.
Mr. G. Is sodium dichromate as strong as KMNO4?
Yep.
So it would do the same thing, convert the
Yeah.
primary alcohol to.
Yeah, so you can either use sodium this one, or you can use sodium dichromate, or you can use chromic acid. Any of these will work.
Doesn't KMNO4 also do like a synaddition of alcohol across the double bond?
Say it again.
I remember it doing a synaddition of alcohol across the double bond. It's like the equivalence of the MCPPA and H3O+.
Isn't that for
Yes,
cancer?
THF.
Is that cancer?
Yeah, so.
Yeah, the proxy acid, that was,
Same thing.
if you have a proxy acid, you can make an epoxide here. To make that diol though, we didn't really look at that reaction. Yeah, because, I mean, there is a reaction where you use, one reaction is use osmine, OSO4, osmine tetroxide, because that'll convert the alkene to a diol, but we didn't look at that. We skipped that one in the chemical.
For the reverse for reduction, is LAH and NABH4 those equal?
Yep.
Okay.
No, LAH is a stronger reducing agent than NABH4.
Okay, that's what.
Yeah, so if you, so get, only these two are, this one and LAH are, see, lithium aluminum hydride. These are both reducing agents, but this is the stronger one.
Right.
That's stronger, that's weaker.
Okay, so oxidizing agents, they're the only ones that have three that are really strong, but the reducing agent LAH is the only one that is stronger.
Now, well, see, there's other ones, because one reaction, for example, the textbook used iron, like any metal is a reducing agent, so you could use that.
Aren't those ketones? Like-
Yeah, they're pretty weak.
And H2 is one. H2, the peroxide, H2, is that oxide?
Yeah, peroxide is a oxidizing agent. That's actually a strong one.
And, okay, is bleach a strong one too, or is it like?
Not as strong as peroxide, but still pretty strong. But see, focus on those. Don't worry about the bleach. For the example, don't worry about these. Worry about the bleaching peroxide if you're doing something at home, like bleaching your clothes or killing bacteria in your kitchen.
It's like when you use hydrogen peroxide to put on blood, it's oxidizing the blood.
Yeah, it's converting. See, what's happening is, that you have the H2O2, and then that enzyme in your blood converts to the H2O and oxygen. So the bubbling is the O2. And I think it's actually H2O2 is killing the bacteria, because I know
It
that.
actually kills all cells, not just bacteria. Hydrogen peroxide, it kills all everything.
Yeah, because I know, that's why that enzyme is present in our blood, because this is very toxic to our, to living tissue.
Yes.
So that's why we got to get rid of this and convert it to water and O2.
RCOR?
Which one?
RCOR?
Yeah, this is, that's a ketone.
Ms. G, using Chem 104, can you oxidize the methyl group sticking out of the rings, or does it have to be aromatic in order for it?
It's got to be aromatic. Yep. Yeah, it's got to be, it has to be aromatic, or you can't do it for like an alkane ring. Yeah. Okay, let's keep on going. This is one of the amino acids, I can't remember which one. So, where will the reaction occur? Yeah, it's not everywhere. Yeah, so figure where reaction occurs, then you can we'll look at what reagents react with.
I think it's most likely to react at the left.
Okay, Rex is running out of film, so it is almost 3 o'clock, so does that mean we have to wrap it up?
Are we going to review during the lab time as well, or are we done?
I'm supposed to be here till 3 to 6 for lab. So that's all of you want to leave, and I have to be here anyway. Yeah, so like I said, figure out where reaction occurs, then we can figure out what reagents will react. So we're sort of doing it the reverse and how we usually do it. So instead of figuring out what reagents react, we'll figure out where reaction occurs first, then we can figure out what reagents react to which reaction.
I would think the reactor is stronger, so there's going to be more.
So it's
Oh,
more
so it's
electrical.
more electrical. That's true.
And then I think this is a leading.
Yeah, they're right.
I don't know. In general, I think this is most electrical. So nuclear power reactors.
I think we'll go H2.
Yeah, I swear this is the next. Teacher's asking us for really. Okay, I picked there. It was S-U, and I wouldn't say it's going to be and I tried this system with I tried to combine and mixed up with the knives.
It's all just pressure. I think you get that idea.
I said it's right.
It's just a matter of worry.
Are you guys getting the principles?
No, I don't know.
I didn't see it.
Okay, so you guys need to take a break and get a snack or something to drink before going on.
They already had a break, so she can sit.
Yes.
Until after this.
Is someone gonna call the cafeteria to take out food?
They'll only salad, so that's it.
I love salad.
I haven't eaten at the cafeteria in years. This one. I don't think I've missed anything. Although they redesigned the cafeteria.
They're overpriced.
Did the, redid the seats.
I went to the lab and finished that.
Where you at the shed, here or the lab?
Here. The lab is not comfortable at all.
Yeah, here's more comfortable. Well, I'm not sure there's another class, but if there's another class, then we'll read it, but otherwise.
Next class is at 6. Which I have.
Yeah, I'm gonna go get them right now. But I also want them to be. I was like, walking up to that.
Yeah, that's why you didn't have to say thank you.
I just saw the one from the photo.
Yes.
Oh, so we're like, we'll come back to this.
Are we gonna come back?
We'll come back here.
And
We will ask